Hey everyone, and welcome. We've all come across those coding problems that seem simple at first glance, but when you dig in, you find this incredible, deep algorithmic beauty. Well, today we're diving into one of the absolute classics, trapping rainwater. We're going to break down exactly how to solve this famous puzzle and do it efficiently. So, let's start with a picture in your mind. Imagine a city skyline, right? A bunch of buildings of different heights all squished together. Now, imagine a huge downpour. Where does all that water go? Well, it gets trapped right there in the valleys between the taller buildings. And our whole challenge, the entire point of this problem, is to figure out the total amount of water that skyline can hold. To make this real, we're going to be working with this exact elevation map for our whole deep dive. Every number you see there is the height of a single building, and we'll just assume each one has a width of 1 unit. You can kind of already see the peaks and valleys just by scanning the numbers, can't you? And for this specific skyline, the answer is 6. 6 units of trapped water. Now, just staring at those bars, it's not super obvious how you'd add up all those little pockets of blue to land on exactly 6. And that is the heart of the puzzle we are about to unravel. So here's the kicker. You could, do some kind of brute force thing, but that would be way too slow. The real goal, the truly elegant solution, is to find that answer, that number 6, by scanning through our list of buildings just one time. But how on earth can you know how much water to trap at any given spot without constantly looking ahead and behind you? That's the real question. Okay, so before we jump into solutions, let's just take a second to formally define the problem. We want to make sure we're all on the exact same page, aiming for the same goal. The official problem statement is this. We get an array of non-negative numbers, that's our elevation map. Our job is to write a function that calculates the total volume of water it can hold. And remember, each bar is 1 unit wide, which actually makes the math a whole lot simpler. Now, before we write a single line of code, there is one simple rule. This one idea unlocks the entire problem. I'm serious, once you really get this, you are 90% of the way to a solution. And here it is. This is the golden rule. For any single spot on our map, the amount of water sitting on top of it is determined by the shorter of 2 walls, the tallest building to its left and the tallest building to its right. Whichever of those two is smaller, that sets the water level. Then you just subtract the height of the building you're currently on, and boom, that's your trapped water. If the result is 0 or negative, obviously there's no water there. So the formula itself, pretty straightforward, right? The real algorithmic challenge, the puzzle, is how do you find those left and right walls for every single position without having to scan the whole array over and over and over again. And that, my friends, is where the elegant solutions come into play. Okay, our first optimal solution uses a fantastic technique called the 2 pointers method. And its absolute killer feature, as you're about to see, is that it uses a constant amount of memory. It doesn't matter if the skyline has 10 buildings or 10 million. All right, let's walk through this. It's super clever. We start with 2 pointers, one at the very beginning of the array, left, and one at the very end, right. We also keep track of the tallest wall we've seen so far from the left. Let's call it left max, and the tallest from the right, right max. Now, at every single step, we ask a simple question. Which of my max walls is shorter? Let's say left max is the shorter one. This is the magic insight. We can now, with 100% confidence, calculate the trapped water at our left pointer's position. Why? Because we know the water level there is limited by left max, and we also know there's a wall on the right, right max, that's at least as tall, if not taller, which seals the container. So we do the math, add it to our total, and just nudge the left pointer 1 step to the right. We just keep doing that, moving the pointers toward each other until they meet. And the efficiency here is just beautiful. The time complexity is O of n, which just means it's a single linear scan. Each pointer only moves forward, so we touch every element once. But look at the space complexity. O of 1, or constant space. We only ever need a few variables for our pointers and maxes. It is incredibly lean and efficient. All right, on to our second optimal solution. This one uses a data structure you might know, called a stack. Now, this approach is a little more abstract, but it's such a powerful pattern that you can actually use it for a ton of other coding problems. It's a great one to have in your back pocket. So, how does this stack thing work? Well, as we go through the buildings from left to right, we use a stack to keep track of their positions, but with a special rule. We try to keep the heights on the stack in increasing order. The second we find a new building that's taller than the building at the top of our stack, ding, 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 we've just formed a water container. Think about it. This new taller building is a right wall. We pop the element off the stack. That's the bottom of our little valley. And the new item at the top of the stack, that's our left wall. Now we have a left wall, a right wall, and a bottom, so we can calculate the trapped water and add it to our running total. And this quote just nails the core idea. The entire game is about using the stack to identify a basin bottom, that little dip that gets trapped between a left wall, which is just waiting patiently on the stack, and a right wall, which is the taller building we've just encountered.
So we've looked at two really fantastic linear time solutions, but which one is the right one to use? Well, let's put them head to head on a final scorecard and see how they stack up.
And when you look at them side by side, the picture becomes really clear. All the best solutions run in O of n time, but they have different memory footprints. The two-pointers method is the undisputed champ when it comes to memory, with its amazing O of 1 constant space. The monotonic stack, and another related approach using dynamic programming, where you pre-calculate all the left and right maxes first, both use O of n space. So if you need pure, raw, memory-efficient performance, you go with two-pointers. But you'd want to study the stack method because that pattern is a key that unlocks a whole bunch of other tricky problems. So let's wrap this all up with the biggest takeaways. First, and most importantly, this entire problem hinges on that one golden rule. Water equals the minimum of the left and right maxes minus the current height. Second, a single pass, or O of n time, is the best you can possibly do. You have to look at every building at least once, right? Third, the two-pointer solution is just remarkable because it hits that optimal time with almost no extra memory. And finally, the monotonic stack is a super powerful, transferable pattern that is definitely worth adding to your algorithmic toolbox. And that brings us to the end. We've totally conquered trapping rainwater in a 1D skyline. But it does leave us with one final and pretty fascinating question to chew on. What if your elevation map wasn't just a line of buildings, but a whole 2D grid of heights? How would you trap water then? Something to think about. Thanks so much for joining me.